Hello everyone, welcome to Business Statistics lecture. For today's lecture, we are going to learn about hypothesis testing for two populations. In previous meeting, we have already learned about how to test a hypothesis for one populations. So we have two populations here, population 1 and population 2. In each populations, it has parameters. We called mu1 for means parameter, sigma square 1 for means parameter for population 1, and pi 1 for proportion parameter for population 1. On the other hand, we also have mu2 as means for population 2, sigma square 2 for variance for populations 2, and pi 2 is the proportion for the population 2. Next, we will have sample here, sample 1 from population 1 and sample 2 from population 2. In this case, population 1 and population 2 are independent. So each of population will be taken sample for also independent case. So population 1 will be taken sample 1 and population 2 will be taken sample 2. In each sample, after we observe or we have n samples as a measure of sample or sample size, then we can compute the x bar 1 as the means for sample 1, as 1 square as the variance for the sample 1, and also we can also compute the proportion for sample 1, which is notated by P1. For sample 2, similarly, we have also x bar 2 for the mean for sample 2, s squared 2 is the variance for sample 2, and also P2 is proportion for sample 2. Based on these conditions of populations, so we can do some of the tests for doing hypothesis testing for two populations. So the first is if the samples or the populations are independent, then we can do hypothesis testing for populations means, and also we can do a paired sample test if the population are dependent, and also we can do population proportions. So the first thing is we can do a hypothesis testing for testing the difference between two means. So if the population means are comes from the independent samples, so we can do a hypothesis testing based on these conditions. So the first condition is both of the standard deviation of the populations are known. The second one is both of the standard deviations are unknown and it assumes equal. And the last one is both of the standard deviations are unknown and both of them are not assumed equal. So we can also actually do an estimation for the difference of the means from mu1 and mu2. And the point estimate for this is the x bar 1 minus x bar 2. So what are independent samples? So independent samples comes from different data sources. These data sources are unrelated one another, and they are independent, which means that they have no connections between these two data sets. Samples are selected from one population has no effect on samples selected from other populations. So this means that these two populations are independent, and samples taken from each of these populations are also independent. And use the difference between two sample means, so we can use these two sample means from each sample to do the hypothesis testing and also estimations for the means. And then we come to the assumptions. So the assumptions can be sigma 1 and sigma 2 are known. And then another assumptions are samples are randomly and independently drawn from the populations. This is the requirement for samples to be able to be analyzed as for hypothesis testing in these two sample cases. The second assumption is the population distribution are normal or both sample size are greater or equal than 30. So this assumption is normal for all of the hypothesis testing because most of the hypothesis testing based on these normal distributions. Since the statistical testing are derived from the normal distributions such as like t statistics and then chi-square statistic and so forth. And then the second assumption is the population standard deviation are known. This is for the first typical of hypothesis testing. So when sigma 1 and sigma 2 are known in both population are normal, so the both sample size are at least 30, then we can use the statistic Z, test statistic Z, and we can also merge this standard deviation for the difference of the means. So the standard deviations of the difference of the means, or actually this is the standard error because it includes n in the formulations, is formulated as the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So if we want to construct a confidence level for mu1 and mu2, we can use this formula. So the interval confidence is constructed by computing the sample means x1 and for sample 1 and x bar 2 for sample means 2, and then we will add and subtract away the z value from the table, statistic table. So the set alpha over 2 is comes from the table set, or you can also use Microsoft Excel to obtain the value, and then it multiplies by the standard error of the difference of means. So we have some steps to construct a confidence interval estimate. The first is define the population parameter of interest and select independent samples from each population. The next step is specify the confidence interval, and the third thing is compute the point estimate. The fourth step is determine the standard error. The fifth is determine the critical value, and the last one is develop the confidence interval estimate. In case of sigma 1 and is sigma 2 are unknown for large samples, we have this type of the second type of assumptions. So these assumptions can be actually quite a little bit similar with the first one. The first assumption is samples are randomly and independently drawn as usual. And then the second is the populations follow the normal distributions. This is also the same with the first, type of populations standard deviations. And the third one is the two standard deviations are equal. So this is quite different with the first one. The first one is similar and the first one is unknown, but the second one is unknown. And for unknown standard deviations, we can assume that both of them are equals for this case. So for another case, we can also assume that both of the standard deviations are not equal. So if the sigma 1 and sigma 2 are unknown, we can use the test statistic, which is t-value, and rather than z statistics, because we do not have any information about sigma 1 and sigma 2. For t-value or t-statistics, we need to specify the degrees of freedom. The degrees of freedom comes from the sum of two sample size from sample 1 and sample 2 minus 2. And we also need to specify the pooled standard deviation, because we have two standard deviations in this case. And to construct the confidence interval, we need to make them as one standard deviations. So the pooled standard deviations is formulated as this formula in the first box, which is square root of n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over n1 plus n2 minus 2. Then we can construct the confidence level for mu1 minus mu2 as below. So this formula is relatively a little bit difference with the first one. The difference are in the t alpha over 2 and also the standard deviation, pool standard deviation, which comes from the mean. And we assume that because the sample size are similar, so we can, if we assume that sigma square is similar, so we just say that these terms and above are s1 square equals with s2 squared. So we can make it simpler just like this. So the third assumption is when sigma 1 and sigma 2 are unknown and they are both not assumed equal. So the assumptions can be derived like this. The first one is population are normally distributed, similar with the previous ones. The second one is there is a reason to believe that the populations do not have equal variances. So this is also the assumptions because actually we do not know the value of the variance. So we just assume that these two variances are not equal. And the last assumptions, samples are independent, just like before. So if the sigma 1 and sigma 2 are unknown and then the samples are small, then if we want to form the interval estimates, the population variances are not assumed equal, so we do not pool them because we cannot do pooling when the variances are different. The test statistic is t-value with degrees of freedom given by the following formula. So the df is the degree of freedom. It comes from the ratio of s1 square over n1 plus s2 square over n2 and all square divided by s1 square over n1 square over n1 minus 1 plus s2 square over n2 all square divided by n2 minus 1. So the confidence level for the mu and mu1 minus mu2 is x bar 1 minus x bar 2 plus minus t alpha over 2 times by square root of s1 square over n1 plus s2 square over n2. So this is a little bit different with the one in when the sigma 1 and sigma 2 are unknown and the variance are assumed to be equal. So in this type of confidence interval, the S1 square and S2 square are stated and also computed differently. Now we comes to the hypothesis testing for difference between two means. We want to test about the difference, whether there is difference of two means, mu1 minus mu2. And we also will apply the same situations like standard deviation known and standard deviations are unknown. And also when standard deviations are unknown, we can also assume that both of them are equal and both of them are not equal. The second assumption is usually used for the small samples rather than the large samples. So these are the formulations of a hypothesis, the null hypothesis and the alternative hypothesis for testing two population means for independent samples. As we learned that there are three types, actually two types in general for the test, the one-tailed test and the two-tailed test. And the one-tailed test divides by two types, the lower tail test and the upper tail test. So for the lower tail test, we will test the null hypothesis mu1 greater and equals than mu2 versus alternative hypothesis mu1 less than mu2. Or we can also write it down by stating like the following null hypothesis. So mu1 minus mu2 is greater and equals than 0, and alternative hypothesis is mu1 minus mu2 less than 0. For the upper tail tests are different in terms of the symbols used in null hypothesis and the alternative hypothesis. So in null hypothesis, it uses less and equal than, and in alternative hypothesis, it uses greater than. While two-tailed hypothesis testing. In null hypothesis, it uses equal signs, and in alternative hypothesis, it uses unequal signs. So another form can also be written down as a difference between two means, mu1 minus mu2, which is equal to 0, or mu1 means minus mu2 unequal to 0. So if we deals with the first assumptions, which is sigma 1 and sigma 2 known, this is for the independent samples. We are going to use test statistics. If we do not know informations about sigma 1 and sigma 2, and they are assumed to be equal, we can use the t-test statistics with the degree of freedom n1 plus minus n2 minus 2. And the last thing is if we do not know about the sigma 1 and sigma 2, and they are assumed to be unequal, so we can also use this test statistic, but we use S1 and S2 as the estimate of two variances, population variances. If sigma 1 and sigma 2 are known, then the test statistics looks like this. So the test statistic for testing the mu1 minus mu2 is using z-test that consists of x bar 1 minus x bar 2 minus mu1 minus mu2 over square root of sigma 1 square over n1 plus sigma 2 square over n2. So this comes from the sample informations, and also sigmas come from the information given in the text, while mu1 minus mu2 is actually the value that we are going to test. So these are steps for testing the hypothesis for two population means. The first step is specify parameter of interest. The second one is formulate the hypothesis. The third one is specify the significance level, alpha, which can be 1%, 5%, or 10%. The fourth step is constructing the rejection region and develop the decision rule. This can be obtained from the normal distributions figures. And the fifth is compute the test statistics and or the p-value. The test statistics are chosen from the appropriate assumptions, whether sigma known or unknown, and sigma are equals or unequal. The sixth step is reach decisions, and seventh is to draw a conclusion. The second assumption is when sigma 1 and sigma 2 unknown, and this is for large samples, then we will use the t statistics, which looks like this. We can observe that the numerator are quite similar with the z statistic for the first testing, but for the denominator is quite different. There is SP, which is the pooled variance from samples, comes from the formula below the box, and times square root of 1 over n1 plus 1 over n2. So, and then for small samples, we can also use this t statistics. And for small samples, we will not assume that the variance are equal. So we will put S1 square and S1, S2 square in the square root because they are different. And the degree of freedom for this test looks like the formula on the bottom box. So hypothesis testing for this mu1 minus mu2, according to the type of the test, will looks like this. This is the box are indicating the hypothesis testing for null hypothesis and alternative hypothesis. For lower tail test, and then the second in the middle is upper tail test, and the right side is the two tail test. When sigma 1 and sigma 2 known, then we will use the set statistics. And as we know that if we use one tail test, we only have one rejection region. Lower tail test will have the rejection region on the left. Upper tail test will have the rejection region on the right side, and two tail sample will have the rejection region on the left and on the right. So alpha indicating the probability which is rejecting null hypothesis when the null hypothesis is true. If we have alpha 5%, then the area under the curve, which is in shades, will have 5% area. This is the rejection region. So if the Z statistic fails in this area, then the null hypothesis will be rejected. Otherwise, the null hypothesis failed to be rejected. The similar thing will apply for the upper tail test. If the Z statistic fail on the rejection region on the right, then the null hypothesis will be rejected. Otherwise, it is accepted. And for two tail tests, if the Z statistic falls in between minus Z alpha over 2 and Z alpha over 2, then the hypothesis will be accepted. Otherwise, the null hypothesis will be rejected. So this is an example of an applications of the hypothesis testing for sigma 1 and sigma 2 unknown, and they are assumed to be equal. So you're a financial analyst for a brokerage firm. Is there a difference in dividend yield between stocks listed on the NYSE and Nasdaq? You collect the following data. So we will test whether NYSE and Nasdaq are similar or different in dividend yield. So if we collect the data, NYSE has 21 as a sample size 1. If we compute the data, we obtain sample mean of 3.27 and the sample standard deviation is 1.30, while Nasdaq has 25 sample size, and if the data is computed, it produces mean of 2.53 and standard deviation is 1.16. So by assuming that the variance are equal, is there a difference in average yield? Test using alpha 5%. So because the sigma 1 and sigma 2 are unknown, then we are going to use standard deviations of samples. And because the variance are assumed to be equal, then we will use the S put in the formula. So we can test like this. X bar 1 is 3.27 as written on the questions. X bar 2 is 2.53. Now mu1 minus mu2 is 0. Why is it 0? Because we are going to test whether mu1 is equal to mu2. If we write in difference way, we will write mu1 equals mu2, but we can also write mu1 minus mu2 equals 0. So if we have mu1 minus mu2 equals 0, so we can replace mu1 minus mu2 with 0. And then we next compute the standard deviations, pooled standard deviations from the samples, and it comes the value of 1.2256. And in the square root, 1 over 21 as the sample size for N1 and 1 over 22 for the sample size for sample 2. And the result is 2.040. If you are wondering about where 1.2256 comes from as the pool variance, you can check underneath. So this comes from the formula written under the lines, the blue lines. So the next step is we will find the critical value of t. So we can find out the critical values of t from the t tables, or we can also use Microsoft Excel to obtain the t values. So you can use the formula of t.inv, comma 1 minus the probability of alpha, comma the degree of freedom. So in this case, if you want to find out the value of t, you just type in Excel minus equals. You can type in Excel in any shell, write my equals t.inv, open bracket, 1 minus alpha, which is 0.05, divided by 2 because this is two-tailed test, and then comma with the degree of freedom of 44 and close bracket. The degree of freedom of 44 comes from the number of sample size in sample 1 plus sample 2 minus 2. So if you do that, you will get the t values of 2.0154. So if we apply it in the figure on the right, so the critical values will be minus 2.0154 on the left and 2.0154 on the right. Previously, we have already got the t statistic is 2.040, and if we check it on the graph, the values fail on the rejection region because it is greater a little bit greater than 2.0154 as a critical value. So the decision is we reject null hypothesis at alpha 0.05. So we have a conclusion that there is evidence that the means are different. And then we move to paired samples. Previously, we discussed about two independent samples. Now, for two paired samples, we can also do a hypothesis testing for test means of two related populations. So paired and matched samples, this is typical of the two related populations. The repeated measures before and after are also an example of two related populations. And for this, we will use the difference between x1 and x2, yeah, because we are going to check whether there is progress from the first step to the second step. So, for example, if we want to check whether the program of diet works or not, then before the diet we will measure the for example the weight or the weight of someone, and then after the diet program the weight will be measured again, and the difference will be measured between the first measurement and the second measurement. So we will test actually the difference between two values, x1 and x2. We have also assumptions for this test. Both populations are normally distributed, or if the assumptions is not fulfilled, then we can use the large samples so that we can say the population is also normal. So if we have already collected the data, then we can also obtain the differences between each pairs. If there are, for example, 20 samples, 20 people who join the diet program, then each people will be measured twice, before the diet and after the diet. And then after that, they will be recorded or subtracted, and we can get the D1, D2, and so forth until D20, because we have 20 people as our sample. So the point estimate is going to be d bar obtained for the sum of the di over n, and the sample of the standard deviation is presented in the box in the bottom. And this is the formula for the confidence interval for d bar. So d bar plus minus t sd over square root of n. So this is actually, we use t statistic for doing the confidence interval construction. Yeah. And SD comes from the previous formula. And to test the hypothesis, we use this t statistics for d bar. For d bar, t equals d bar minus mu d over SD over square root of n. And SD comes from the previous formula. And the degree of freedom of t is n minus 1. So these are the formulations of hypothesis for null hypothesis and alternative hypothesis. Actually, this is quite similar with the one in independent sample test. There are three types of tests: lower tail test, upper tail test, and two-tail test. But the differences are in the formulation of the hypothesis, which is this. In this case, we only state mu d greater than 0, mu d equals or less than 0, and mu d equals 0. This is an example for the pair sample test. So assumes you send your salespeople to the customer service training workshop. Is the training effective? And then you collect the data like following. So for example, we have 5 salespersons indicated by these initials CB, TF, MH, RK, and ML. So the number of complaints are recorded before and after the training. So before the training, the CB got 6 complaints, while TF got 20, MH have 3, RK has no complaints, and MO has 4 complaints. After training, the number of complaints are recorded again, and it looks like that the number of complaints decreased for almost all of the salesperson. Next, we will subtract the number of complaints after the training and with before. So for CB, the difference of after and before is -2, comes from 4 minus 6. For TF, the difference is -14. It comes from 6 minus 20 and so forth. So we'll get the difference for all of the salesperson. If we add, difference of DI, the result is -21. Then we can apply some of the formula. We can find the d bar from the sigma di over n, which is -4.2. So it comes from -21 divided by 5, because there are 5 salespersons. And then SD comes from the DI. DI is the value of the difference between the value of difference for each salesperson with the mean. And then all square, and then they're being summed n over by n minus 1. If we square root this, we will get the SD equals 5.67. And then we can continue the hypothesis testing by looking at the critical value, because we use T statistics, so we also need to look at table T in statistical books, or using T.inv to get the value of T tables. In this case, we use the degree of freedom is 4, comes from n minus 1, because we have 5 salespersons, so we subtract 5 with 1, which is equal 4. Next, we will have T statistic comes from d bar minus mu d over sd over square root n. D bar is -4.2, while mu d is equal to 0, because in the null hypothesis, we see that mu d equals 0. So we put 0 on the formula. Next, we substitute SD with 5.67, comes from the previous calculations, and the square root of 6 is square root of n is square root of 5 because the number of salespersons is 5. And finally we got the t statistic here is minus 1.66, and then we check whether the t statistics lies in the acceptance region or in the rejection region. We see in the figure that minus 1.66 is greater than the critical value, which is minus 2.7765. That means that the null hypothesis does not be rejected. So in another meaning, or in other words, that there is no difference between the number of complaints before training and after training. So in other words, conclusions, there is not a significant change in the number of complaints. So that is all for today's lecture. I hope you understand what that I have explained to you for today's meeting, and I'll see you for the next meeting. Bye.